Okay, folks, this is chemical catalysis, which is our last topic in the kinetics chapter. All right, we're going to look at a couple of things in this section. We'll look at how catalysts work, and we'll talk about two different kinds of catalysts, homogeneous and heterogeneous. And those terms can refer to the catalyst itself, or it can refer to the catalytic process. So we could say this reaction is taking place with heterogeneous catalysis or homogeneous catalysis, or we could say a homogeneous catalyst was used or a heterogeneous catalyst was used. So that adjective applies to both the catalyst and the process. All right, and then we're going to look at just a couple of examples. All right, so first thing, how does a catalyst work? What a catalyst does, remember one of our previous lectures, we plotted this reaction coordinate, in which we had our reactants here and our products here and energy on that y-axis. And we said that there is some kind of an energy barrier going up to this high energy transition state, and that energy barrier is called the activation energy. And the rate constant is related to that activation energy barrier. The lower the activation energy barrier, the higher the rate constant. The higher the barrier, the lower the rate constant, and of course the slower the reaction. So if you have a reaction that looks like this, when it's uncatalyzed, what a catalyst does is it provides a different reaction mechanism, and that different reaction mechanism has a lower activation energy barrier. And so the reaction profile for the catalyzed reaction looks like this, with that lower barrier. And if the activation energy for the catalyzed process is lower than for the uncatalyzed process, then the rate constant is going to be correspondingly faster. Right? Okay, a couple of other points I want to make about these about catalysts, right? And we'll look at this specifically in the examples that follow, but I just want to make a couple of points. All right. All right. So first thing is catalysts participate in the rate determining step, but they're not part of the balanced reaction. Let me put another word in there. Not part of the balanced net reaction. Right. So they do play a role in the mechanism by providing a rate determining step with a lower activation energy, but when you add up all of the steps of the reaction mechanism, the catalyst does not factor into the net reaction. Often what happens is the catalyst is consumed in an early step, but then regenerated in a later step, so it ends up canceling out and it doesn't appear in the net reaction. Okay. And so that brings us to step 2. Okay. Catalysts are not consumed in the reaction. They participate in the steps of the reaction, but ultimately they're not consumed in the reaction. And so a catalyst can continue to work over and over and over and over again. So a small amount of catalyst can be used to catalyze a very large amount of reactants. All right, let's take a look here. Okay, so one more thing. First, there are 2 types of catalysts: a homogeneous catalyst, and that just means that the catalyst is in the same physical state as the reactants, and usually this means in solution you have a dissolved catalyst reacting with other species dissolved in solution, or for gas phase reaction you can have a gas phase catalyst, right? For heterogeneous catalyst, the reactant and the catalyst are in different states, and in this case, I can't think of any examples where this is not the case, actually. I guess it wouldn't have to always be this way, but every example I can think of follows this, and that is catalyst is usually a solid, right? So we'll see some examples of solid catalysts in the examples that follow. First, let's take a look at a homogeneous catalysis, decomposition of ozone. This is an important reaction in the upper atmosphere because ozone screens out ultraviolet rays and helps prevent people from getting skin cancer. So we want to keep as much ozone in the upper atmosphere as we can. And ozone is constantly undergoing a series of reactions in which it's being created by some reactions and being destroyed by other reactions. And this over here on the left, this is the process by which ozone is normally destroyed in the atmosphere. And that is, you've got a molecule of ozone, O3. One of those oxygen-oxygen bonds splits apart, so you get an oxygen and a lone oxygen atom. Right? That lone oxygen atom is very reactive, so that bounces around a little bit, and when the lone oxygen atom encounters another ozone, it causes that ozone and oxygen atom to break apart to give you 2 oxygens. Right? And so the net reaction is 2 ozones giving you 3 oxygens. All right. Now this reaction has something that we've seen before. In fact, we may have seen the same reaction before. Right? This species here remind you that species is intermediate. It's something that's created in an early step and then consumed in a later step. Right? So it's a part of the reaction, but it doesn't show up in the net reaction. Okay? We'll see catalysts in just a minute. Catalysts are slightly different but very similar. Right? Also, I'll mention that this first step here, this first step is very slow. Breaking that oxygen-oxygen bond is difficult, and so that's the rate determining step here. Now, one of the problems that started happening in maybe the 50s, 60s, and 70s is people started using a lot of chlorofluorocarbons for refrigerants and aerosols and things like that. That got a lot of chlorine-containing compounds into the atmosphere, and when those chlorine-containing compounds break down, they produce isolated chlorine atoms. And those chlorine atoms in the atmosphere can catalyze the destruction of ozone. And the way this works is a chlorine atom reacts with an ozone molecule to give oxygen and this ClO molecule. Okay, and this reaction here is faster, has a lower activation energy barrier than this reaction over here on the left. Right. Once the chlorine reacts with ozone to make O2 and ClO, the ClO molecule can then react with another ozone to make 2 molecules of oxygen and regenerating that chlorine atom. Okay. So, and let's say this, once you take these equations and you add them up, we've got a ClO here, a ClO here, those cancel, got a chlorine here and a chlorine here, those cancel, and so our net reaction is this. Notice that this reaction for the catalyzed process is the same reaction as we have for the uncatalyzed process. If the two reactions aren't the same, then it's not truly a catalyst. Okay? A catalyst, as I said before, by definition, isn't part of the balanced net reaction, so those two reactions have to be the same. Okay? All right, I want to look at this a little bit more. Okay. So we've got two interesting species in this catalyzed reaction, right? We have this ClO that's produced in an early reaction and consumed in a later reaction. So just as before, this is an intermediate, right? But we've also got this chlorine here, which is used at an early step in the reaction, so it's consumed, it's a reactant, and then it's reproduced as a product in a later step. Okay. And so that's our catalyst. Okay. And notice that as this reaction goes, the chlorine is important for speeding up the reaction by providing this low energy rate determining step, but the chlorine is then reproduced later in the reaction, so it can come back and do the same thing again. It goes through the cycle, comes back and does it again, right? So the concentration of ozone will decrease over time, but the concentration of chlorine stays constant, right? That's one of the properties of catalysts, that a small amount can catalyze a large number of reactants. If it's a process that you want to happen, that's a good thing, right? If it's a process you don't want to happen, like the destruction of ozone, then that's a real problem, right? So as a result, chlorine-containing chlorofluorocarbons and things like that have gradually been reduced. The use of them has been gradually reduced since the 1970s, and we've got a lot less chlorine in the atmosphere than we did 20, 30 years ago. And the ozone hole, don't really hear much about it anymore. When I was in college, ozone hole was a big topic. People were talking about that all the time, almost as much as people talk about global warming today. But you don't hear about it that much because we've eliminated a lot of the chlorine in the atmosphere, and so that catalyzed process is not as important as it was a few decades ago. All right, let's look at another homogeneous catalysis. I didn't mention this on the last page, but the chlorine is a homogeneous catalyst because the reactants were gases and the chlorine is a gas, right? The same thing is true here. This one is in solution, however, and here we're looking at the decomposition of hydrogen peroxide. Hydrogen peroxide, like we have in the lab and like you can buy at the drugstore, will spontaneously decompose to give you water molecules and oxygen. The process, as shown here, right, is very, very slow, particularly because of this second step here that has a very high activation energy. It's a complicated step involving two molecules have to come together in just the right way in order to break bonds and form new bonds. And so it's got a high energy transition state. And as a result, this decomposition is very slow. So if you buy some hydrogen peroxide at the drugstore and you put it in your medicine cabinet, it'll gradually go bad. You know, maybe 5 or 10 years from now, it'll be noticeably inferior. But generally speaking, it'll last a pretty long time. And even though it's producing oxygen, you won't see any evidence of oxygen production if you just look at the solution. You can catalyze this reaction, though, by adding iodide. That should be a superscript. Should be a superscript there. You can catalyze this by adding iodide ions, and that gives you this lower energy rate determining step here, forming this hypoiodite ion. And the hypoiodite reacts with another hydrogen peroxide to make water, oxygen, and reproduces the iodide. So just like in the previous example, right, the iodide, which is the catalyst, is a reactant in an early step in which it's consumed, and then it's a product in a later step so that it's regenerated, and as a result, the concentration of iodide remains constant throughout the reaction, and the catalyst is not consumed. And the decomposition of hydrogen peroxide is a catalysis demo that people use a lot. You've probably seen it before. I wanted to try to get a video of it to put in here, but I can't seem to make the video embed function work in this PowerPoint. But the reaction, you've got your hydrogen peroxide in a little beaker, and it's gradually producing little bubbles of oxygen, right? And it produces bubbles of oxygen so slowly that you can't even see them, right? But if you add a catalyst, it produces all of those oxygen bubbles really, really fast. And if you add a little bit of soap to it, then those bubbles will turn into a foam. And so what you see here is what happens if you take a solution of hydrogen peroxide and you add a little bit of soap to make it foamy, and then you add iodide. All of the oxygen bubbles form immediately, and it makes a foam that just shoots out the top of the flask. Like I said, you've probably seen this on TV or on videos or something like that. Maybe your high school teacher did it. If not, go on YouTube and do a quick search on elephant toothpaste. You'll probably find 20 videos of it. Somebody recently did one where they're trying to break a record, and they set one up that they claimed was the biggest one ever, and did this in a swimming pool, and it filled the entire swimming pool with foam in about, I don't know, like 10 or 20 seconds. It was pretty amazing, actually. So anyway, if you get a chance, go check these out on YouTube. They're kind of cool. All right, now heterogeneous catalysis is when the reactants and the catalyst are in two different physical states. Okay? And usually the physical state is a solid. Right? So here's a typical reaction. You'll study this when you get to organic. It'll probably be in the first couple of weeks of the class. It's a reaction people always talk about early in the organic chemistry class. And this is the hydrogenation of ethylene, right? So ethylene looks like this. You got a double bond here, and bring in a hydrogen molecule, and this double bond can break to make ethane, like that. All right, so that's what the reaction is, right? And of course, this bond here would have to break as well. That's the reaction we're talking about. This reaction, as it is very, very slow. So if you take a container of ethylene and you put some hydrogen in it and you let it sit there for a long time, it's not going to do anything. You're not going to have any noticeable reaction converting to ethane. Right? But if you add a catalyst, and the catalyst in this case is a metal, usually platinum, and we have a catalyzed reaction, we usually write the catalyst above the arrow like that. So if you do this reaction, mix these two ingredients in the presence of platinum, then the reaction goes very rapidly, and you can get very efficient conversion of ethylene to ethane. Okay, we'll see how this works. What happens is you've got a metal surface here, and the ethylene comes in and gets near the surface. This double bond in here breaks, and it forms kind of a weak chemical bond to the metal surface here. And the hydrogen does the same thing. As the hydrogens come in and get near the metal surface, the bond between the hydrogen weakens, and bonds between the hydrogen and the metal strengthen, right? So that basically takes the hydrogen molecule, the H2, and breaks it up into two individual hydrogen atoms. And then once you have these two individual hydrogen atoms, they can come and interact with those carbon atoms, right? That's what's being shown here and here. Those hydrogens interacting with the carbon atoms to form this new product, right? So it's the ability of the hydrogen molecule and this ethylene molecule to interact with that metal surface, which weakens the bonds and allows the old bonds to break, and makes it possible for new bonds to form. Okay. I'll mention something else too in this. When we talked about zero order reactions, we talked a little bit about saturated catalysts, right? And we said zero order reactions tend to occur when you have a catalyst that's saturated. So this would be a really good example of this, since the reaction has to occur on that surface, right? If you've got tons and tons and tons of hydrogen and tons and tons and tons of ethylene, the reaction is not going to go any faster if you have a limited surface area, right? Because it can only go as fast as the molecules attached to the surface react and then deabsorb or desorb from the surface, right? So the rate of the reaction is going to be dependent on the surface area of this catalyst, much more so than it is the concentrations of the reactants. As long as that surface area is constantly covered, okay, then it'll be saturated. Okay, a second kind of heterogeneous catalysis is what happens in catalytic converters in an automobile. And this is a catalytic converter, and it is inserted in the exhaust system. And what it does is it catalyzes three important reactions in the exhaust stream. Right? One of them is the combustion of any unburnt fuel. Right? The fuel generally would react with oxygen in the engine, and would be converted into CO2 and water. And this reaction is downhill energetically, right? So the CO2 and water are more stable than the unburnt fuel, and so it ought to naturally go in that direction anyway. But sometimes the fuel just isn't in the cylinder long enough, and the combustion is incomplete, and a little bit of unburnt fuel goes through and gets into the exhaust. And if that gets into the atmosphere, it can cause pollution. It's an important component in the formation of smog and things like that. So we want to get rid of that. And what the catalytic converter does is it speeds up, catalyzes, right? Catalyzes this reaction by converting all of that unburnt fuel to CO2 and water. Right? Another thing that happens in the catalytic converter is the oxidation of carbon monoxide to CO2. And again, CO2 is more stable than carbon monoxide, so the reaction would normally run downhill, right? And we would normally expect everything to form carbon dioxide, but if the reaction is incomplete, or if maybe there's just not enough oxygen getting into the engine, then instead of everything going to CO2, you'll produce significant amounts of carbon monoxide. And carbon monoxide, of course, is toxic, so you want to get rid of that. And the last thing is the decomposition of nitrogen monoxide, right? Nitrogen monoxide is a really important pollutant. This is probably the most important thing in the formation of smog. And once it gets into the atmosphere, the NO can react with oxygen to make NO2, and this NO2 is, let me write it like this. That's almost the right color. This NO2 is an orangey brown gas, and if you ever see a picture of a city with a bad smog problem, you'll see that there's kind of an orangish brown haze over the city, and that haze is due to NO2. And the NO2 is formed from NO in automobile engines. So in order to reduce the smog, which it's orange and nasty, it just looks gross, but it's also a real bad eye, nose, and throat irritant. It's just really nasty stuff. Anyway, so to get rid of the smog, we want to try to get rid of the nitric oxide in the exhaust. And again, the products, nitrogen and oxygen, are more stable than the NO, so the reaction should spontaneously go in that direction, but sometimes the reaction is just incomplete, and so we need the catalytic converter chamber in which the reaction can speed up to make sure that it goes all the way to completion before it comes out the tailpipe. Okay, so this is what the inside of the catalytic converter looks like. And this is, I'm not sure how well this picture is going to come out, but this is called a honeycomb, right? And what it is, like I said, I'm not sure how well you can see the picture, but if you can imagine getting about 50 or 60 drinking straws and then just holding them all together so you have a whole bunch of tubes lined up, that's what this is. And so all of the exhaust goes through here, and it goes through these holes and then travels through that whole block of material inside that catalytic converter. And the reason that it's shaped like that is to increase the surface area. Right? If you had one tube like that and your gas was going through, there'd be a very, very small contact between the gas and the sides of the tube, right? But if you had a whole bunch of little tubes and the gas is going through there, it would have much more contact with the walls. And that's what we're looking for here, because the walls of that honeycomb structure is where the catalytic material is. The catalytic material, by the way, in a catalytic converter in the exhaust system, this part here is usually made of some kind of a ceramic, but then it has a coating on it which contains precious metals including things like platinum, palladium, and rhodium. And all three of these are very expensive. And so this is why catalytic converters are very expensive. And it's also why people used to, I'm not sure if this still happens as often as it used to, but maybe 10 or 20 years ago, there were problems in big cities of people parking their car, going into their apartment at night, and while they were asleep, someone would come in with a hacksaw and go underneath the car and actually cut the catalytic converter out of the exhaust system and steal it because they were so expensive because of all these precious metals. And the way this reaction works, just like with the hydrogenation of ethylene, right? We'll just look at that last reaction, the decomposition of nitric oxide. Right. So that's the reaction that we're looking at. And the nitric oxide has a triple bond, which is fairly strong, right? So there's a very high activation energy barrier to try to take that nitric oxide and break that bond to form nitrogen and oxygen. But when these come down and interact with this, these little bits of palladium metal in that honeycomb structure, as the nitric oxide reacts with the palladium and absorbs on it, it begins to form a little bit of a bond here with the palladium surface, and as it forms that bond, the bond between the nitrogen and the oxygen weakens, and if there's a neighboring molecule here which is also adsorbed on the surface, right, then this nitrogen can interact with that nitrogen, this oxygen interacts with that oxygen, and the two things leave and desorb off of that surface as a nitrogen molecule, and an oxygen molecule. And it's this interaction here on that surface, that heterogeneous catalyst, that allows that to happen. All right, great. So this was a slightly shorter video, which is good, right? And the things we talked about here that I want you to know is that catalysts work by providing a different reaction mechanism, and that different reaction mechanism has a lower activation energy. And since you remember the rate constant has this relationship here, the Arrhenius equation with the activation energy, the lower the activation energy, the higher the rate constant. So if you can provide a different reaction pathway with a lower activation energy barrier, the reaction is going to go faster. The catalysts participate in the rate determining step, but do not appear in the balanced reaction. That's because for heterogeneous catalyst, it's usually some kind of a surface effect, so the catalyst is not consumed. For homogeneous catalyst, the catalyst is usually consumed in an early part of the reaction, but then reproduced in a later part of the reaction. And so, as a result, catalysts are not consumed in the reaction, so catalysts can keep working over and over and over and over again. You don't have to replace them, that's good. And finally, we can classify catalysts as being homogeneous or heterogeneous. All right, that's it for catalysis, and I think that's actually it for the kinetics chapter. So take a look at this. You should be able to do all of the problems in the kinetics study guide at this point, so please be working on those, and I'll see you in the next one.